Welcome to the start of Unit 2, starting with Section 1.4, Slope and Rate of Change. Let's take a look at the following example before we start defining the term slope. In this problem, we're told Jim traveled 258 miles on 12 gallons of gas. Sarah traveled 182 miles on 8 gallons of gas. Which car gets the better gas mileage? In order to figure out which car gets the best gas mileage, we want to figure out how far each car can travel on just 1 gallon of gas. The way we can do that is through division. Now, starting off with Jim, he travels 258 miles on 12 gallons of gas. If we take 258 and divide by 12, we get 21.5. 21.5 represents how many miles he can drive per gallon. Now, we'll do the same thing for Sarah. Sarah can drive 182 miles on 8 gallons of gas. So 182 divided by 8 gives us 22.75. So Sarah can travel 22.75 miles per gallon. Well, the car with the best gas mileage will be the car that can drive the farthest on the same amount of gas. Well, Jim only travels 21.5 on 1 gallon of gas, while Sarah travels 22.75. So Sarah gets the best gas mileage. What we did in the last example is we found the ratio of how far each car can drive to how much gas is in the tank of the car. Such ratios we refer to as the slope. If we consider 2 points on the line, which we're going to call x1, y1 and x2, y2, as we move from x1, y1 to x2, y2, the slope is the following ratio. It is the change in the y coordinates over the change in the x coordinates. Another way we can write this, instead of writing change in, we replace that with this triangle-looking symbol, which is the Greek letter delta. So the change in the y coordinates is delta y, the change in the x coordinates is delta x. We call the change in the y coordinates the rise, and the change in the x the run. So the slope is the ratio of rise to run, which can also be calculated as y2 minus y1 over x2 minus x1. y2 minus y1 would be the rise, x2 minus x1 would be the run. What's special about the slope is if we're working with a linear model, no matter what 2 points you give me on that linear model, the slope will always be the same value. Linear models are the only models where if you take any 2 points and calculate the slope between them, the slope will always be the same. In this example, let's compute the slope of a line that passes through the points P, which is going to be the 0.63, and Q, which is the 0.43. Recall from the previous slide that the slope of a line is y2 minus y1 over x2 minus x1. It does not matter which point you make x2, y2 and x1, y1. Usually, I would make the first point x1, y1, the second point x2, y2. Once when you've designated which point will be your first, which will be your second, throw the values into your formula to calculate the slope. So our slope is going to be, throwing the values into our formula, y2 is 3, minus y1, which is also 3, over x2, which is 4, minus x1, which is 6. And if we work this out, we get that our slope is 0. Next, we're going to use Desmos to determine the slope of each linear equation. Let's start off with 3x plus 5y equals 15. First, we're going to enter our equation into Desmos, so that way we can see the graph. Now that I see the graph, you want to identify 2 points on the graph. I'm going to use the intercepts here, because Desmos highlights the intercepts nicely for us, but any 2 points can do as long as you can identify what their coordinates are. Think about us traveling from the point 0,3 to the point 50. What would be our rise? What would be our run? Well, if I start at 0,3, I would have to travel to the right 5 units. So if we were to calculate our slope, my run is 5, and it's positive because I went to the right. If I went left, I'd make my run negative. Then I want to count down till I hit the 0.50. Well, when I go downwards, I go down 3. Since I went down, my rise is going to be negative, and more specifically, negative 3. Since my slope is rise over run, my slope will be negative 3 over 5. Now we're going to find the slope of 2x minus 4y equals 9. I've already entered the equation here into Desmos, and you can see the graph here in purple. If we highlight our x and y intercepts, to travel from the 0, negative 2.25, to the 4.50, I would first go up 2.25 units. So my slope, I would start off with here, the rise being positive 2.25. Now, what would be the run? Well, I would have to travel to the right 4.5 units. And since I'm traveling to the right, that would be my run, and it would be positive. Now we can take the 2.25 divided by 4.5 and enter it into our calculator. And when we do, we get the slope is 1/2. And it is best to write your slope as a fraction just to see clearly what the ratio of rise to run is. You can see with the fraction, every time I move right 2 units, I have to go up 1 unit. Now we're going to determine which of these tables represents a linear function. Recall from before that in order for a function to be linear, the slope is constant, meaning for any 2 points on the graph of the function, or in this case the table, the change in y divided by the change in x should always be equal. Another way to interpret that is if x is changing by the same value. In these tables, you can see the x are all changing by 5s, going from 0, 5, 10, 15. Then f of x should be changing by some fixed value as well. May not be the same as what x is changing, but it is still changing consistently. So taking a look at the first table, again, notice how the x's are increasing by 5 from row to row. If we take a look at the f of x, we're going from 2 to 4 to 6 to 8. So each time x increases by 5, f of x is increasing by 2. So the slope would always be 2/5. This table does represent a linear function because the slope is constant. If we take a look at the second table, x is increasing by 5 each row, but g of x, from the first to the second row, we're increasing by 6. The second to the third row, we're increasing by 18. Well, I don't even have to check the last row. We can see that the y's are not changing consistently, even though the x's are. So if I take a look at these 2 points, I'm going to have one slope. But if I take a look at these 2 points, the slope will be different. The first slope would be 6 over 5. The second slope would be 18 over 5. So can this function be linear? No, the slopes are not constant. Going to the third table, the x's are still changing by 5s. H of x, we can see its value is decreasing by 5. So whenever x increases by 5, h of x is always going to decrease by 5. So this is a linear function. And the slope will always be negative 5 over 5 or negative 1. In the third table, the x is still changing by 5. But notice in the f of x column, the value of f of x stays the same. So no matter how much I change x by, f of x is always going to be the same. This is perfectly fine. Indeed, this function is linear because every time x increases by 5, f of x is increasing by 0. In other words, the slope would be 0 over 5, which is 0. We call this kind of linear function constant because it never changes. In our fifth table, still changing by 5, but notice how in the g of x column, we increase by 2, decrease by 2, then increase by 2. So our g of x is not changing consistently, even though our x is. So can g of x here be a linear function? No. And for our last table, x's are still increasing by 5, and our h of x, from our first to second row, we're increasing by 25. From our second to third, we're increasing by 75. Well, that's enough for us to determine that h of x is not a linear function. What can the slope tell us about the graph of our linear equation? Now, we know linear equations are always going to be lines. If the slope is positive, that means the rise and the run have the same sign. So the dependent variable will increase as the independent variable increases, or the dependent decreases as the independent variable decrease. On the other hand, if the slope is negative, then the rise and the run have opposite signs. Then the dependent variable decreases when the independent variable increases, or it will increase when the independent variable decreases. And third, if we get a slope of 0, then the dependent variable is constant. If we take a look at the figure below, our first graph is where the slope is positive. And notice how the rise and the run, as we travel from point P to Q, we're going right and up, meaning the run is positive, the rise is positive, we have the same sign. This creates a line that is increasing. If we take a look at the second graph, notice how to travel from P to Q, we run to the right, but we fall downwards, meaning we have a negative rise. Well, the rise would be negative, the run would be positive, making the slope negative. And this creates a line that is decreasing. If our slope is 0, well, we're not rising, we're only running, meaning we're only traveling from left to right, which creates a horizontal line that we see here. The second thing the slope does is it measures the steepness of a line. As the slope gets closer to 0, the line is less steep. As the slope gets farther from 0, the line becomes steeper and steeper. If we take a look at this last figure here on the right, if we go from a slope of 1/2, 1, 2, and 5, as our slope gets farther from 0, notice how the line is getting steeper and steeper. Same thing goes as we become negative, but farther away from 0. Negative 1/2, negative 1, negative 2, negative 5. Again, as we get farther and farther from 0, our line gets steeper. What are some phrases that we can use instead of slope in application problems? The first that usually pops up the most are phrases such as rate of change. The rate of change just describes how fast something is changing. As we change the independent variable, how much does that impact the dependent variable? The second word we may associate slope with is steep. And these usually deal with problems with roadways, ramps, or railways. And you may also hear the word grade instead of steep. Grade is another way of saying how steep something is. The third phrase we may hear is scaling factor. This is usually used more when dealing with maps or blueprints. And lastly, speed and velocity, which is usually used a lot when you're dealing with problems involving moving from one location to another. So let's take a look at the following example. We want to know which is steeper. First, a railroad track A with a 1.2% grade, or a railroad track B with a slope of 1.23. The first thing we see is the word steep. Remember, steep is one of the phrases That means slope. So what is this problem telling us? Well, which is steeper? Which has the greatest slope? Now, grade is another word we can use to interchange with the word slope. Now, one thing to be careful of is we don't like to work with percentages or compare with percentages. Looking at the 1.2%, keep in mind we don't like to work with percentages. What we're going to do is we're going to convert the 1.2% into a decimal. One thing to recall is percent is Latin for per 100. So 1.2% is the same as saying 1.2 over 100, which is equal to 0.012. So railroad track A has a slope of 0.012. Taking a look at track B, we're told track B has a slope of 1 over 23. However, comparing a fraction can be a bit difficult to do. The easiest way to compare numbers is if they are in their decimal form. So if we take our calculator and do 1 divided by 23, we get 0.043. Now let's go back and answer the question. Which of these railroads is steeper? Well, Railroad A has a slope of 0.012. Railroad B has a slope of 0.043. 0.043 is the larger slope. Therefore, B is the steeper railway. In this example, we're going to see how slope can help us answer a few questions. My car can travel 200 miles with 5 gallons of gas. We want to figure out two things. How many miles can I travel with 7 gallons of gas? And how much gas will I need to travel 15 miles? Now, in this problem here, gas would be the independent variable. The miles would be the dependent variable because the distance my car travels does depend on how much gas is in there. So if I want to think about the slope formula with my specific variables, my change in the dependent variable would represent how far I can travel. My change in my independent variable would be the amount of gas I have. So at the very start, before answering this question, let's start off looking for the slope. In other words, how far can I travel divided by how much gas I have? In this case, 200 divided by 5. And when I divide 200 by 5, I get 40, meaning I can travel 40 miles per gallon. Now let's answer our two questions. How many miles can I travel with 7 gallons of gas? Our slope 40, we know has to equal how far we can travel over how much gas I have, which is 7. Now I have a little mini equation. If I multiply both sides by 7, I get that the distance I can travel is 280 miles. For the next question, how much gas will I need to travel 15 miles? Well, if we set up our slope formula, we know our slope is 40. Now here we're told how far we want to travel, so 15, but we don't know how much gas we need. So 40 equals 15 divided by our amount of gas. Now this time we're trying to solve for gas, but we do want to get it out of the denominator. So we're going to multiply both sides by the amount of gas we need. 40 times the amount of gas we need equals 15. Well, to finish solving, we can divide both sides by 40. You'll need 0.375 gallons of gas to travel 15 miles.